Okay, good afternoon, guys. We'll get started. So I do apologize, I have a bit of a cold today, so if I sound funny, that's at least one of the reasons. All right, so last time we were talking about equivalence relations. We defined what an equivalence relation is. It's a relation that's reflexive, symmetric, and transitive. And I started talking about these things called equivalence classes. And the observation was that whenever you have an equivalence relation over some set, that equivalence relation partitions the set based on which elements are equivalent under the definition of that relation to each other. So let's talk about that. I started this example last time. Let R be the relation A comma B such that A and B got the same grade in this course. And we'll say, whoops, every time. And we'll say that this relation R is over the set of students who are enrolled in this course. All right, so first, is this thing going to be an equivalence relation? So is it reflexive? Yes, because you got the same grade as yourself. Is it symmetric? Yeah, if you got the same grade as me, I got the same grade as you, and it's transitive for basically the same reason, right? It's transitive for all the reasons the regular integers are transitive. All right, so this thing really is an equivalence relation, so that's one observation. So that's good to know. And it also partitions all of the students into these classes. Right? There's the set of all students who got an A+, the set of all students who got an A, an A-, and so on. So R partitions the students in this class into sets, or into classes. So the students who got an A, the students who got an A, whatever, so just an A as is, and then so on, all the way down to F, but of course there will be none of those this term. All right, so there's nothing special about this relation R. It's an equivalence relation, and that's the thing that matters. Any equivalence relation does this. So let R be an equivalence relation on a set A. The set of all elements related to R, related by R to little a, is called the equivalence class of little a. So the set of all elements A in big A related by R is the equivalence class of A. Sorry, the set of all elements B in A related by R to A in A is the equivalence class of A. Okay? And we denote this in a special way. We put A in square brackets and a subscript R. Sometimes we leave out the R if the R is clear from context, right? So if I'm only talking about one relation, if I put it in square brackets, it must refer to that relation. All right, so if I wanted to be explicit about this, the equivalence class of A over the relation R is the set of all B's such that AB is in the relation. Okay, this is the equivalence class of A. It's all the things that are equal to A. All right, so if B is in that equivalence class, we say that B is a representative of the equivalence class. And any member of the class can be chosen to be a representative. So A would be just as good a representative for this class. This might seem weird now. We'll do some examples, and hopefully it'll be a little bit better. So let's see some examples of these things. So let's say R is the set of pairs AB such that A equals B or A equals minus B. Right? This is something we've seen a lot. And let's say this is over the integers. So I think we showed it last time that this is indeed an equivalence relation. If not, it's not too hard to believe that it's reflexive, symmetric, and transitive. All right. So because it's an equivalence relation, it has these equivalence classes. So an integer is equivalent. And when I say equivalent here, I mean equivalent with respect to the relation R to itself and its negative. Right? So 1 is related to 1 and minus 1 by this relation. So this relation considers them to be equivalent. So let's start looking at the representatives. For any integer A, we have that the equivalence class of A is equal to A and minus A. Those are the things that it is equal to. So for example, the equivalence class of 1 over the relation R is 1 and minus 1. The equivalence class of 2 in the relation R is the set 2 minus 2. What about the equivalence class of 0? Yeah, it's just 0. There's no minus 0. That's exactly equal to 0. All right, so that's good. Any questions about this? Is this okay? All right, so let's do another example. This is something we haven't really seen before. So let's say R is the set of pairs AB such that A and B have the same first letter. And this relation is defined over the set of all English words. Okay, so is this thing going to be an equivalence relation? I mean, probably, right? I'm doing it in a section on examples of equivalence relations. So any word has the same first letter as that same word. If a word has the same letter as same first letter as another word, then that is also true in reverse, and it's also true transitively. And if you don't believe me, sit down and work it out. So this is an equivalence relation. Which is nice. And what are the equivalence classes of this relation? What are the equivalence classes of R? Yeah?
Word starting with A, word starting with B, word starting with C.
Yeah, exactly. So one class is the set of all words in English that start with A. Another class is the set of all words in English that start with B, then C, then D, then so on. So the equivalence classes of R are, well, one is the set of all words in English starting with A. And then the same thing starting with B, C, all the way down. So there are 26 equivalence classes here, assuming we ignore upper and lower case. All right. So one thing you can notice here is that there's something very special about this subdivision. I've already talked about it. In this last example, every word in English fits into exactly one of these equivalence classes. Right? Every word starts with a letter, because every word has at least one letter in it. So there's always a first letter, and it's got to be one of the 26 letters of the alphabet, so it has to be in one of these classes. So that's one nice thing. And the other nice thing is that if you take the union of all of these equivalence classes, you get back the original set that the relation is defined over. So this relation is defined over the set of all English words. If you take the union of all of these classes, you get the set of all English words. Right, so it's a disjoint partition. Right, so that actually that is what a partition is. So everything fits into exactly one, and what that really means is everything fits into at least one and at most one. All right, so that's nice. So the equivalence classes form a partition of the set over which the relation is defined. So this is a partition, and that's a word I've been using but haven't really defined thoroughly. So I'll do that now. So two classes are either equal or disjoint. Right? So there's no overlap. If you took two classes, they're either equal or disjoint. So if we go back to this example here, where it's a equals b or a equals minus b, the equivalence class of 1 and the equivalence class of minus 1, they're not disjoint, but that's okay because they're equal. Right? They're exactly the same. So two classes are either equal or disjoint, and the union of all classes is exactly the set over which the relation is defined. So there's two parts of being a partition, right? The first is that different things in that partition are either equal or disjoint. There's nothing in between. There's no partial overlap or anything like that. And the other thing is that when you take the union of all of them, you get back whatever you started with. That's what it means to be a partition. So one thing that's really neat is that this actually works in the other direction too. So if I gave you a partition of a set, you can define an equivalence relation whose equivalence classes are that partition. So let's talk about that a bit. So given a partition of a set A, well, we can always construct an equivalence relation R on A such that the equivalence classes of R make up that partition. So let's do an example of that. Question first?
Do those three properties, the reflexivity, symmetric, and
Gotcha.
transitivity, do they like guarantee that every member of A is going to be in the relation?
Yeah, so as soon as you know that it's an equivalence class, that guarantees that, do you mean the members of the set the relation's defined on?
Yeah.
Yeah, they have to be because it's reflexive, right? So every single thing in that set is in there somewhere. Yeah. All right, so let's do an example. Let's say we have this set A, and it's 1, 2, 3, 4, 5, 6. And notice I haven't said anything about relations yet. I'm just talking about the set. And I'm going to partition it into A1, which is 1, A2, which is 2, 3, and A3, which is 4, 5, 6. So A1, A2, A3 is a partition of the set A because no two of them are equal, right? All of them are either equal or disjoint. And if I take the union A1, union A2, union A3, I get back A. So this really is a partition. And now what I'd like to do is define an equivalence relation on A that has those equivalence classes. So I want to define an equivalence relation R on A with equivalence classes A1, A2, and A3. So this is the opposite problem, right? Initially, we were given a relation and we wanted to figure out what the equivalence classes were. Now I give you the equivalence classes, I want to know what relation has those equivalence classes. All right, so the way you do this is you define a mini relation over each one of the sets in that partition, and then you take the union of all those three things. So I define R1 to be the following. It's AB such that A and B are in A1. Okay? So A1 is just 1, so this is just 1 comma 1. Now I go to R2, and I do the same thing. It's AB such that AB is in R2. So now I look at R2. R2 is 2, 3. So how many things am I going to have in R2? 2, 3. Do I have 4? Yeah, that's 4. Because each thing could either be the first thing or the last thing, or both. So I get 2, 2, 2, 3, 3, 2, and 3, 3. Is that okay? Yeah. Yes, sorry, A2. All right, so now we'll go on to R3. It's the exact same trick. AB such that AB is in A3. And how many things are going to be in this one? 9, exactly. So this is a little bit more work now, so I like to go kind of carefully and in order. So I'll start with the 4s. I get 4, 4, 4, 5, 4, 6, 5, 4, 5, 5, 5, 6, and 6, 4, 6, 5, 6, 6. Right, if you go sort of in order like that, it's easier to make sure you have them all. All right, so that's good. Does anyone see why it's 9 things here? Because you're making pairs. There's 3 choices for the first thing, 3 choices for the second thing. 3 times 3 is 9. All right, you'll learn more about that in 2804. So now the relation R we want is R1 union R2 union R3. So that's 1, 1, 2, 2, 2, 3, 3, 2, 3, 3, 4, 4, 4, 5, 4, 6, 5, 4, 5, 5, 5, 6, and 6, 4, 6, 5, 6, 6. And now if you stop and think for a second, it's not too hard to believe that this thing is going to be reflexive, and it's not too hard to believe that this thing is going to be symmetric, and it's a little bit more work, but hopefully you'll be able to give yourself that this thing is transitive as well. And for sure what happens is that we have these equivalence classes that we wanted. Because the only thing related to 1 is 1. That's the only time 1 appears. The only time 2 appears is in some kind of relation with 3. And that's what happens in R2, and similarly for R3. So that's why it has these equivalence classes. Okay? Any questions about this? So the main thing to remember when you're looking at these equivalence, at this partition, you want to come up with the classes or vice versa, things in those sets in the partition, they need to be related to everything else in that set. All right, so that's everything I want to say about equivalence classes and equivalence relations. We're ready to move on to the next kind of relation, and that is the partial order. So these are also called partial orderings. So when we look at equivalence relations, we looked at symmetric, reflexive, and transitive. For partial orders, we're going to look at something slightly different, and I'll talk about it in a second. So relation R on a set A is called a partial order, or sometimes a partial ordering, if it satisfies three conditions. It has to be reflexive, it has to be symmetric, or sorry, not symmetric, antisymmetric, and it has to be transitive. So it's almost the same as an equivalence relation, except instead of symmetry, we have antisymmetry. Okay, that's the difference between an equivalence relation and a partial order. All right, so we have some extra notation for these. So a set A, together with a partial order R, on that set, I should say. Well, that's called a partially ordered set. And typically that's abbreviated to POSET. And it's denoted A, R. Members of A are called the elements of the POSET. So this isn't really anything new. I'm just giving more names to things that we already know. So typically we talk about the relation. But you can also talk about the set that the relation is defined on. So that's all we're doing here. Before we name the relation, now I'm also talking about A. So R is the partial order, A is the partially ordered set. That's all this is saying. Is that definition clear? It's not clear why we care yet, but this is the definition. All right, so let's see some examples of these things. So the greater than or equal relation on the set of integers is a partial order. Okay, so to see that, we have to check, is it reflexive? And the answer is yes, because A is greater than or equal to A for all integers A. That's definitely true. Is it antisymmetric? Well, remember, the definition of antisymmetric is an implication. So we assume the thing on the left and prove the thing on the right. So the thing on the left says AB is in R and BA is in R. So in our particular case, that would mean assume A is greater than or equal to B and B is greater than or equal to A. And we have to show that A equals B. Is that true here? Yeah, if A is bigger than or equal to B and B is bigger than or equal to A, the only way those can be true simultaneously is if A equals B. So this thing really is antisymmetric, because that's the definition of antisymmetric. And then the last condition I have to check is transitive. So transitive, again, it's an implication. So you assume that A is bigger than or equal to B, and B is bigger than or equal to C. And what I'd like to do is prove that A is bigger than or equal to C. And is this going to be true? Yeah, because you can just sub in to get A is greater than or equal to C. Right? You just sub in C for B, and everything's fine. All right, so this is a partial order. What about greater than? Is greater than going to be a partial order?
No, it's not reflective.
Right. Greater than is not a partial order because it's not reflexive. Because, for example, 1 is not greater than 1. 1 is equal to 1. So based just on this example, it might seem weird that we're calling it a partial order. Because we know that you can compare any two integers. So that's actually something called a total order. The reason it's a partial order is because we don't actually have this requirement. Okay? Before I show you an example of that, I want to do one more example here. So the other example I want to do is this divides relation. So the divides relation on the set of positive integers, we already saw that it's reflexive and transitive. Right? We already saw that. Is it antisymmetric? So to refresh your memory, last class we showed that divides was not an equivalence relation because although it was reflexive and transitive, it was not symmetric. So the question I'm posing now is it antisymmetric? Any ideas? Yes. So in fact it is. So we already know that it's reflexive and transitive. So if I can show that it's antisymmetric, then I know it's a partial order. So the answer is yes. We assume A divides B and B divides A. And what I'd like to show is that A equals B. So if A divides B, then I know that B equals K1A for sure. And if B divides A, then I know A equals K2B. So far so good? All right, so let's write down another way of writing B. So B equals K1A, and I know that A equals K2B. So B, whoops, K1 times K2B. Right? All right, so that's good. So I know that B equals K1 times K2 times B. What does this tell me? Right, so if I cancel the B's from this side, I get 1 equals K1 times K2. All right. Why am I allowed to cancel those B's? I'm allowed to cancel them because they're positive integers. If it were possible that B was 0, it wouldn't make sense to cancel them because then I would be dividing by 0. But I know that B is a positive integer, therefore it's valid to divide by it. All right, so if K1 times K2 is 1, what do I know about K1 and K2? They can't both be positive. Why not?
Or they have to. The only possibility that it's going to be 1 and 1.
Right, so why is that?
Because you can't multiply two positive. If you multiply two positive integers, you'll get a positive integer that's greater than both of them, unless it's 1 and 1.
Okay, so you're on the right track. So the only way we could get 1 would be if either K1 and K2 are both 1. So that's the case we're hoping for. The other way is, well, either K1 or K2 would have to be bigger than 1, which means the other one would have to be smaller than 1, and there isn't anything smaller than 1 that's a positive integer. Okay, so that's why. So K1 times K2 has to be 1, and therefore K1 and K2 are exactly the same thing. They both have to be 1. Okay, so that's great. Why do we care that K1 and K2 are 1? Yeah, so I can sub this fact in up there or up there, and therefore A equals B. Doesn't matter which one you sub it into, both of them will give you the same answer. All right, so that's good. That means this thing really is antisymmetric because the only way that we have A divides B and B divides A is if A equals B, and that's exactly the definition of antisymmetry. All right, so this example, whether or not we believe it yet, shows that partial orders really are partial. That's an important part of it. You can't always compare two elements in the partial order. So I'll say exactly what I mean there. In a partial order, we cannot always compare two elements. Some partial orders you can, but not all of them. All right. So let's talk about that. The elements A and B are comparable if they're related in some order. Oops. So think about how these work. These partial orders sort of have like a less than or equal feel to them. And what I'm saying is that they're comparable if one of the two ways you can write the pair is in the relation. So for example, under the less than or equal relation, 1 and 3 are comparable because 1 is less than or equal to 3, or 1 is not less than or equal to 3. So another way of saying that is 3, sorry, that's not what I mean. 1 is less than or equal to 3, or 3 is less than or equal to 1. That's what I mean to say. So in that relation, all pairs of elements are comparable because we know a lot about the less than or equal relation. But it doesn't have to be that way. Sometimes pairs can be incomparable. So when neither AB is in R nor BA is in R, we say that A and B are incomparable. So let's see an example of that. So in the divides relation, 5 does not divide 7, right? 7 does not divide 5. So this relation can't put them in order. It doesn't know how they compare to each other. So we say in the divides relation, 5 and 7 are incomparable. On the other hand, 2 divides 4. 4 doesn't divide 2, but that's okay. I have one of the pairs, and therefore 2 and 4 are comparable. So this isn't like less than or equal. In less than or equal, we always know that one number has to be less than or equal to the other number. Right? That's how you compare integers. But in a partial order, that's not required. Sometimes you have elements that you don't know how they compare. Is that clear to everyone? So the fact that we can have these things is why they're called partial orders. If you did have the case where every two elements were comparable, then what you actually have is a total order. So a total order is a partial order where every pair of elements is comparable. Yeah?
Is it possible that an element is not comparable with itself?
No, because it has to be reflexive to be a partial order. Okay, so I'll just make a quick note of that. If all pairs of elements are comparable, the relation is a total order. Sometimes this is called a chain. That's another word for it. And we say that the set itself is linearly ordered. And we also call the set totally ordered. So there's lots of other names for a lot of these things. know why it is that way, but it is. All right, so that's what partial orders are all about. And I'd like to now turn our attention to the idea of representing partial orders. So if we go back to the first class and we started talking about relations, I said there was a bunch of ways to represent them. So we had this table representation, a matrix representation, some graphical representations. I'd like to go back and talk more about the graphical representation. And this brings up what's called a Hasse diagram. That's H-A-S-S-E. All right, so we can represent partial orders graphically using a special tool called a Hasse diagram. And the idea is if you just sat down and did a regular, so one of those diagram representations, you end up drawing a lot of stuff. It gets really messy really quick, and I'll show that to you in a second. All that a Hasse diagram does is simplify that diagram by assuming that you have a partial order. Because if you know that you're working with a partial order, then you know that a lot of connections in that diagram have to be there. Right? So for example, you have loops going from one thing back to that thing, and that's everywhere because partial orders have to be reflexive. So if you leave a bunch of things that you know have to be there out, the diagram becomes simpler, but hopefully still usable. All right, so the idea is to draw the relation as a graph. And graphs are actually the topic of this course immediately after this one. So this is kind of a nice lead-in for it. Graphs, I'll give you a sneak preview. Graphs have two elements. They have vertices and they have edges. And edges go between two vertices. So the way these work is that you have a vertex for every element in the set. And you have an edge to denote which elements of the set are related by the partial order. All right. So let's look at this. Suppose we had the following poset. Say it like this. The less than or equal relation on the set 1, 2, 3, 4. Okay, so we already know that's a partial order. So I'm going to draw it out graphically. So I'll say this is 1, 2, 3, 4. And now I start drawing edges. So I know that 1 is related to 1, because 1 is less than or equal to 1. I know that 1 is less than or equal to 2. I know that 1 is less than or equal to 3. And I know 1 is less than or equal to 4. So far so good? All right, so now I'm going to start with 2. I know that 2 is less than or equal to 2. 2 is less than or equal to 3. And 2 is less than or equal to 4. Okay. 3 is less than or equal to 3. And 3 is less than or equal to 4. And finally, 4 is less than or equal to 4. So this is awful, right? This is so bad. We took something that was really, really simple, the less than or equal relation, and destroyed it with this awful diagram. Right? If you saw this diagram, it's not at all obvious that this is what less than or equal to looks like. Right? This is really bad. So we don't like to display partial orders in this way. There's a better way to do it. So we can simplify this in a few ways. The first way is, well, we know that partial orders are reflexive. So we can remove these self-loops, right? The one going from 1 to 1, from 2 to 2, 3 to 3, and 4 to 4. So let's do that. now I have this. Which is a little better, I guess. Still not great, but we're making progress. What else do I know about partial orders? Yeah? Transitivity. So I have a lot of these edges that I know have to be there because of transitivity. So for example, I have an edge from 1 to 2, and I have an edge from 2 to 3. That's redundant because I know that I can get from 1 to 3 because it's transitive. So having 1 to 2 and 2 to 3 is enough. I don't need to add that 1 to 3 edge. So simplify, again, partial orders are transitive. So we can draw it like this. I have 1, 2, 3, 4. I'm going to draw 1 to 2, 2 to 3, and 3 to 4. Have I captured everything I possibly need to now? Yeah, right? So let's look at the edges that were long. The long edges were 1 to 3. Can I get from 1 to 3? Yeah, I go 1, 2, 2, 3. The other long edge was 1, 4. Can I get from 1 to 4? Yeah, I go 1, 2, 2, 3, 3, 4. And finally, 2, 4. Can I get from 2 to 4? Yeah, I go 2, 3, 3, 4. So this is a little bit different now, because now to figure out if two pairs are related, we have to follow a bunch of edges instead of just following one edge. But if you're just looking at this thing, this seems more natural, right? It feels more like a less than or equal relation. So is it clear how I got to this point so far? All right, so I still don't love this diagram. I still don't love this diagram because we haven't taken advantage of one more property. What's the last property of a partial order? Yeah? Yeah, it's antisymmetric, which means I'm never going to have arrows going in both directions. Right? Arrows always go in one direction only. So wouldn't it be nice if I didn't have to draw any arrows? Right? That would simplify the diagram a bit more. I need one rule though if I'm going to leave off the arrows. Yeah?
You could say like arrows always go up.
Yeah, if I just say arrows always go up, then I can just leave them off. Right? If I just say don't draw the arrow, then it's not clear which direction it goes. But if I say they always point up, then I can leave them off. So simplify. Partial orders are antisymmetric. And therefore, arrows only go in one direction. And let's say that direction is up. So now I can draw it like this. And that's a much better diagram than what we started with. Right? This is very, very simple. You can clearly see the pattern. But it only makes sense if we remember that we're dealing with a partial order. So these Hasse diagrams are only for the case when you're working with a partial order. It doesn't make sense to do these for things that are not partial orders. So don't go drawing one if there's an equivalence relation or something else. Does that make sense? Yeah?
Why can't we do it with equivalence?
Right, so you can do the initial step I did with an equivalence relation. You just can't do this last step. So the first two simplifications are fine with the equivalence relation. Can't do the last one, but it's not called a Hasse diagram. It's just a graphical representation. I don't think that has a special name. All right, so it's perfectly fine to do all of your relations like this, but if you have a partial order, then this is much simpler. All right, so it doesn't always work out this nicely, right? This is a very simple Hasse diagram. It's a line. It gets more interesting. So let's do another one. I'm going to look at, I'm going to look at the divides relation over the set 1, 2, 3, 4, 6, 8, 12. This one's a little bit more complicated. All right, so let's start from scratch. This is a little bit tricky. One, 2, 3, 4, 6, 8, 12. What does 1 divide? 1, but also 2, 3, 4, 6, 8, and 12. So that's the first one. This is not the Hasse part. I'm starting from scratch for this. Okay, so that takes care of 1. What does 2 divide? 2 divides itself. It divides 4, 6, 8, and 12. All right. What does 3 divide? 3 divides itself, 6, and 12. What does 4 divide? 4 divides itself, 8, and 12. 6 divides itself, and 12. 8 divides itself, and 12 divides itself. Question? All right, so this is obviously really ugly. So let's try to do a little bit better. We know that 1 divides a lot, so it has a lot of arrows going up, which means 1 should be at the bottom. So I'm going to put 1 down here. So this is 1. And now I look at the things that 1 divides. Well, 1 divides everything. So let's start with 2. I'm actually going to do this a little bit further down just to give myself some room here. So this is 1. 1 divides 2, which is great. 1 also divides 3. 1 also divides 4, but so does 2. So I can put my 4 up here. All right, what's next in the list? 6. Where do I put 6? Yeah, I need 2 things, but that's okay. There's nothing wrong with that. So 6 is divisible by 2 and by 3, but not by 4. All right, so now I look at the next thing in my set, 8. 4 divides 8, so that seems like a logical spot for it. Nothing else does, at least not that isn't connected to 4. And then the last thing is 12. This seems like a good spot for 12. 12 is divisible by 4 and by 6. So this is one possible Hasse diagram for the divide relation over this set. And this is much prettier than the other thing, right? That's a much better way of representing the information. Any questions about this? Yeah. What do you mean the other thing?
Well, like, because that's another path before. You go from
6, 3, 1. So remember though, the arrows are always going up, so you never want to go down the chain. Yeah. Yeah.
If 0 were in the set, would it do 1.50?
Okay, so let's look at this. A divides B if and only if B equals C times A for some C. So you're asking if 0 divides or something divides 0?
If 1 divides 0.
Okay, so does 1 divide 0? Well, that would be if 0 equals 1 times C. So is there a C that does that? 0. Other questions? All right, so that's one Hasse diagram. Let's do another one. I want the subset of relation over the power set of ABC. Bet you thought you'd never see that again. Same thing. So what is the subset of ABC? Or sorry, the power set of ABC? Well, this is just the empty set A, B, C, AB, BC, AC, ABC. Right? And there's 8 things in there, not too surprisingly. And one subset is going to be related to another subset if it's a subset, which I guess sounds a little bit confusing. One element of the power set will be related to another element of the power set if it's a subset of the second element. All right, so what should probably go at the bottom here? Yeah, it's going to be the empty set. You want something that's not below it in this relation. And below means basically sort of like a smaller set, but also you care about the elements that are inside of it. So the thing at the bottom should always be the smallest in some sense, and the smallest thing here is the empty set. So the empty set goes at the bottom. And now I look at what are all the things that are a little bit bigger than that in some sense. So what is the empty set a subset of? Well, go in order. The empty set is a subset of A, it's a subset of B, and it's a subset of C. All right, so now let's get a little bit bigger. What is A a subset of? Well, A is a subset of AC. It's also a subset of AB, so I can do those connections. As it happens, sorry, I'm going to change this diagram a little bit just so it looks nicer. I'm going to put C in the middle, otherwise these lines start to cross and it gets ugly. Sorry about that. So A is a subset of AC and AB. There's also the subset BC over here, and it's a subset of B and C. All right, and B is also a subset of AB. And furthermore, C is a subset of AC. Have I got all of them? Question? Exactly. So now I do one more up here. A, B, C. AC is a subset, AB is a subset, and BC is a subset. So if you haven't done what I corrected there and put them in a different order, that's completely fine. You still get a perfectly valid Hasse diagram. It just doesn't look as pretty. You kind of like it when there aren't too many crossing lines, because when lines start to cross a lot, it gets a little bit confusing, or at least it does to me. We'll talk about that a lot more when we start talking about graphs. So this is the Hasse diagram for this power set of ABC with the relation subset of. Questions? All right, so now that we have a new thing to talk about, we have all sorts of terms for these things. So one of the big benefits of these diagrams is that it's easier to pick out certain special elements. So I'll say one benefit of Hasse diagrams is that it is easier to pick out certain special elements. So we have a whole bunch of special elements. So I'm going to do a whole bunch of definitions now. So an element A is maximal in a poset S I'll say in a poset A with order with partial order R if the following is true: there is no B in A such that R, A, B. So somehow A is the biggest thing. And at this point, I'm going to change this notation a little bit to make it easier for you to understand what's going on, because I don't really like this notation. I find this confusing, and I'm going to change it slightly, and you'll all find it much easier. So instead of saying R, I'm going to say a different thing. I'm going to say this sort of special less than sign. It's like a cursive less than sign. And that's the symbol I'm going to use, a cursive less than or equal sign, I should say. That's the symbol I'm going to use for a partial order. And I like this because it's sort of like less than or equal to. So just remember less than or equal to is a partial order. And now this is kind of like a fancier version of that looks like something else. And now that you see it this way, it's much easier because this thing here is really just A is less than B. So A is somehow the biggest thing. There's no B that's bigger than it is. Yeah?
What's the word that is like to pick out?
Easier to pick out certain special elements, yes. Yeah, no, that's my fault. Okay, and there's one more condition here, and that is and A is not the same as B. So that is another important condition. So if I ever have A is less than or this fancy less than or equal to B and A is not equal to B, I'll just write it this way. I'll just write A is less than B. I like that notation better because in my mind it's easier to remind myself that this is what maximal means. There's nothing bigger than it. There's no B such that A is less than B. A is the biggest thing. That's what it means to be maximal. Okay? Is that clear? If you don't like that notation, just stick with the other one. It's fine with me. So an element A is minimal in a poset A with order less than or equal if there is no B in A such that B is less than A. So an element A is minimal if there's nothing smaller than it. And this matches up with the usual definition of minimal. Does this make sense? All right, so now that we have these Hasse diagrams, it becomes much easier to find these things. Where does the maximal element live? Where does the minimal element live? Right, so that's what it sort of feels like intuitively. What it really means is that the maximal element doesn't have anything leaving it from above, and the minimal elements don't have anything entering it from below. As you do more and more examples, you'll see that you can't just look at the top and look at the bottom, because you could have something like this, right? If you had a partial order that looked like this, then this is a minimal element, that's a minimal element, and that's a minimal element. It's really easy to forget about that minimal one. It's not that it's at the bottom, it's that there's nothing coming from below into it. That's what makes it minimal. And similarly for maximal. Okay, so that's an important exception to remember, because that tricked a large number of people on last year's final exam. Okay, so having these diagrams makes it much easier to find those. So in a Hasse diagram, the maximal element or elements have no edges leading up, and the minimal elements have no edges leading down. So notice that there's no single minimal or single maximal element. And if you don't believe me, let's look up at this divides one. What are the maximal elements here? 8 and 12 both have equal claim. And notice that 8 and 12 aren't comparable. So in divides, eight and 12 are maximal. What's minimal? 1. What about in the power set example? What's maximal? Yeah, and what's minimal? Yeah. So in the power set example above, A, B, C is maximal, and the empty set is minimal. So it's important to remember that you might have more than one. It could be more than one. Will you always have at least one? Yeah, so why do you have to always have at least one? Yeah? Yeah. So one question you could ask yourself is, well, maybe something happens if the relation doesn't have anything in it. So the empty relation of partial order? So let's say the empty relation of the set 1, 2, 3. Is that a partial order? No? Why not? Yeah, it's not a partial. That's a simple example. So whenever you give definitions like that, you should always check to see if it makes sense when there's somehow nothing to be talked about. Yeah? Right, so I haven't yet talked about this case in a lot of detail. So all of the Hasse diagrams I'm talking about are for finite process. Yeah, that does break down for infinite process. Yeah?
Had a set, you got a relation before the empty set on the empty set. Would that mean?
So again, that's not, so you're defining a relation on the empty set?
Yeah.
I guess, I don't really know what it means to define a relation on an empty set. I guess as I presented the definitions, that would make sense. Yeah, so that's a weird one, I guess. Yeah, it wouldn't have a lot of meat to it. All right, so the next thing I want to talk about after maximal and minimal elements are greatest and least elements. So sometimes there is an element that is larger than all other elements. And this is called the greatest element. Okay, and what this means is that B is less than or equal to A for all B in S. And if that happens, then A is the greatest element. So can I have more than one greatest element? No, why not? So this says for all B in S. Or I guess A is the set I used earlier. Stay consistent. Right? You can't have that because it's quantified over absolutely everything. So if it's greater than everything, it's comparable to everything. And that's the key difference. Before I didn't require that because I wasn't looking at all the pairs. Now I am. It has to be comparable to everything. In the divides example, we had two maximal elements, and they're not comparable. So in fact, in that case, we don't have a greatest element. Okay, so you might not have one. If you have one, it's unique. Okay, so similarly, sorry? So you're talking about if you had a relation that was just a single element? Exactly. All right, so you can also define the least element. And when you do, that's called a least element, if it's smaller than all other elements. Okay, so what that means is that A is less than or equal to B for all B in A. So both the greatest and least elements are unique when they exist. So if they don't exist, there's none of them. So if you're doing a question that involves asking something about the greatest and least elements, your answer should only be one element. If it's more than one element, you've done something wrong. All right, so let's see some examples. In my in my divides example, is there a least element? What is it? It's 1. Is there a greatest element? No, because there's 2 maximal elements. Right? And if there's 2 maximal elements, they're not comparable, which means neither of them is the greatest. In the power set example, is there a least element? Yes, the empty set. Is there a greatest element? Yes, ABC. So really what you do is you look at all the minimal elements, all the maximal elements, and if there's only one minimal, then there's a least. If there's only one maximal, then there's a greatest. All right. So I'll just write those down quickly. In in divides, 1 is minimal. Oops. And there's no maximal. And in power set, empty set is minimal. And A, B, C is maximal. All right, so that's good. There's some more notation that we can also use, and this is when you want to look at minimal and maximal, but only in one part of the post set. Yep. Yes, I do. We'll chalk that one up to the cold. All right, so to do this other thing, you might want to bound a subset of the post set for reasons we might see a little bit later. So given a post set A with partial order less than or equal, I define 2 things. So if U is in A and A is less than or equal to U, I have to fix my definition here a little bit. So given a post set S with a partial order less than or equal to and a subset A of S, if U is in S and A is less than or equal to U for all A in A, then A is an upper bound of A. So all this is saying, this is a lot of notation, it's weird. So all this is saying is if you have some subset of your post set and there's something that's bigger than everything in it, that's an upper bound for that post set. That's all that definition is saying. Okay, and we can also go the other way and talk about lower bounds. So if L is in S and L is less than or equal to A, sorry, this should be U as the upper bound, not A. and L is less than or equal to A for all A in A, then L is a lower bound of A. So this says the exact opposite. If you have some subset of your poset and there's something that's less than or equal to everything in it, then that's a lower bound. Is that definition clear? Sorry, I changed the notation a bit because I know I hated the possible. So if this doesn't make sense, I'll do an example and then hopefully it'll be clear. So I'm going to define this Hasse diagram. So I have A at the bottom, and then C, B, D, E, G, F, H, and J. So don't worry about where this comes from, and I'll add in some edges here to make it a little bit more interesting. Don't worry about where that comes from. This is just some diagram. I'd like to know about a bunch of these things. So let's start with upper bounds of A, B, C. So to answer these questions, I suggest you highlight the subset you're interested in. So I'm interested in A, B, C. So A, B, C. And I want to know what are the upper bounds of A, B, and C. So what are all the things that are bigger than everything in that set? So let's go through and ask ourselves, is D an upper bound of this set? No, so why not? Right, I can't get from C to D. C and D are incomparable, so D can't be an upper bound for a set involving C. Okay, what about E? E is, because E is comparable to B, C, and A, and it's bigger than all of them. So E is definitely in there. What about F? F is in there for the same reason. What about G? No, because I can't get there from C. And remember, when I say get there, I mean get there only going up, right? Because I can only follow arrows in the direction they lead, and we said all the arrows point up. What about H? H is fine. And what about J? J is fine as well. So those are the upper bounds of A, B, C. What about the lower bounds of A, B, C? Yeah, it's just A. So this is something that's very easy to forget. If I ask you for the lower bounds or upper bounds of a set, that could include something in that set. That is a possibility that you need to account for. That didn't happen in the first example because B and C were both bigger than A. So they weren't going to be an upper bound because B and C were not comparable. In this example, though, A, B, and C are all comparable. A is comparable to B and A is comparable to C, and it's smaller than both of them. So that means A really is a lower bound for A, B, C. Does everyone see that? If you maybe forget, then just remember that there's a self-loop from A to A, and maybe that will jog your memory. Okay, what about upper bounds of HJ? So now we're looking at something else. Whoops. Right, HJ are both at the top. There's nothing above them, which means they could only have an upper bound if they were comparable, but they're not comparable, so there is no upper bound. There's no upper bounds of H and J. What about lower bounds of H and J? So A, C, E, and F, that's true. Anything else? D and B. Okay. What about G? So it's not going to be G because I can't get from G to J, going only up. For everything else, I can get from A to H and A to J going only up. So I have all of those, but nothing else. So essentially this is everything except G and then H and J because they're not comparable. All right, let's do another one. What are the upper bounds of A, C, D, F? So let me highlight these. A, C, D, and F. What are the upper bounds of A, C, D, F? So it's going to be J, H, anything else? So this is the trick I told you about a second ago. Yeah, F is also an upper bound, because even though it's part of the set, it's comparable to everything else in the set, and it's bigger than all of them. So F is an upper bound of that set, and that's something that's really easy to forget. What about the lower bounds of A, C, D, and F? Right, in this case, it's just going to be A, right? Nothing else, because, well, the only other things that would even remotely make sense would be B and E. It can't be B because B and C aren't comparable, and it can't be E because E and D aren't comparable. All right, so there's one more piece of notation we need, and that's this last property. There's also the idea of being a least upper bound and a greatest lower bound, and it's exactly what you would think. So if A is less than or equal to X for any X in A, and X is less than or equal to Z for any upper bound Z of A, then A is the least upper bound of A. And again, this is a situation where the definition is really ugly, but what's happening is fairly straightforward. So I'm going to do the other one, and then I'll show you some examples, and hopefully that'll make it easier. So if Y is a lower bound of A, and Z is less than or equal to Y, whenever Z is a lower bound of A, then Y is the greatest lower bound of A. Again, really ugly. So let's do examples. I want the greatest the greatest lower bound of, let's say, BDG. So let me highlight those for us. BDG. What is the greatest lower bound of BDG? B. What are all the lower bounds? B and A are the lower bounds. The greatest lower bound is B. Okay, so lower bounds are A and B. And then, just to continue this down here, what is the least upper bound of BDG? What's the least upper bound of BDG? G, even though H is also an upper bound. I'm interested in the least upper bound. So the least upper bound of BDG is G, and the upper bounds are G, comma H. So the kinds of questions you'll see here are obvious, right? I'll give you a Hasse diagram or a relation, and I'll ask you which each of these things are. All right, that's it for